I'm Rajesh Uppal, Director IDST. We bring sharp insights and foresight on defense, security, and emerging tech. Let's dive in.
Imagine a world where we can watch atoms move in real time, where we can actually see electrons shifting, vibrating, and reorganizing themselves as a material changes its behavior. This isn't science fiction anymore. It's the emerging reality unlocked by quantum microscopy, a breakthrough that gives scientists a new window into the invisible world that governs our most advanced technologies. For decades, we knew that the tiniest atomic movements could trigger massive effects in quantum materials. A material could flip from an electrical insulator to a superconductor, or rearrange its electronic waves in trillionths of a second. But even though these transformations shaped the future of energy, computing, and materials science, no tool existed that could capture them as they happened. Traditional microscopes offered sharp detail but moved too slowly. Ultrafast lasers captured rapid events but lacked atomic precision. This created a kind of resolution paradox. We could see space or time, but never both. And the secrets of quantum materials live exactly where those two worlds collide. Now quantum microscopy is breaking that barrier, combining ultrafast lasers, quantum sensors, and atomic resolution probes to capture a true molecular movie of electrons and atoms in motion. Scientists can trigger changes with a quick pulse of energy, then track how atoms react and how electrons reorganize, not in theory, but in stunning real-time detail. One of the most remarkable demonstrations of this came from Sebastian Loth's team in Germany. They studied a material called niobium selenide, famous for hosting a wave-like pattern in its electron density, something known as a charge density wave. This collective motion of electrons is incredibly delicate. One impurity, one misplaced atom can disrupt the entire electronic rhythm. But no one had ever actually seen that disruption happen. Until now. Loth's team used picosecond electrical pulses to nudge the electron wave and push it toward a single impurity. And for the first time, they watched the wave deform, ripple, and finally stall as it collided with that defect. To capture these faint distortions, they built a quantum microscope capable of repeating the measurement 41 million times per second. Think of it like filming electrons in slow motion, revealing a world so subtle and so fast that it was once completely hidden from science. And this isn't just a scientific curiosity. These discoveries have enormous implications. In high-temperature superconductors, quantum microscopy can reveal exactly how electrons pair up and move without resistance, a key step toward room-temperature superconductors that could transform global energy systems. In quantum computing, it lets researchers see how atomic defects disrupt fragile qubit states, offering a pathway to error-resistant quantum processors. In Spintronics, it shows how electron spins interact with atomic lattices, unlocking more efficient and more powerful memory and logic devices. Even aerospace systems, which require electronics that survive extremes of temperature and radiation, may one day rely on materials engineered with atomic-by-atomic precision thanks to insights from this technique. But perhaps the most revolutionary impact is this. Quantum microscopy turns materials science from discovery into design. Instead of stumbling upon new materials by chance, scientists can engineer them intentionally, shaping atomic arrangements, tuning electronic motion, and sculpting quantum phases with unprecedented control. It opens the door to catalysts designed atom by atom, solar materials that harvest light with perfect efficiency, and quantum devices built from precisely orchestrated electron waves. For the first time in history, we can finally watch the atomic dance that defines the material world. And by understanding this dance, frame by frame, we gain the ability not just to observe nature, but to shape it. Quantum microscopy marks the beginning of a new era, one where the invisible becomes visible, where electrons tell their own stories, and where the future of technology is written at the smallest scales imaginable. The atomic world is no longer hidden. We're finally learning its choreography, and the innovations it unlocks could shape the next century of science and engineering. Thanks for watching. Subscribe, follow, or visit idsth.com for more cutting-edge defense and tech insights. See you in the next one.